Hello friends, how are you? How the things are going on? It may be very difficult and also you are feeling very bored for this prolonged quarantine period, but it is mandatory. It is mandatory for the good health of individuals. It is mandatory for the good health of family members. It is mandatory for the good health of our nation and the whole world as well. And hence we have to strictly adhere to the stay home, stay safe policy for few more days. During this quarantine period, I come up with another chapter of hydraulics and pneumatics for a revision purpose. It is the second unit, that is dynamics of fluids. In the last video, we discussed about the first chapter, that is introduction to hydraulics, in which we studied the properties of the fluids which is at rest. In this chapter, dynamics of fluids, which carries 25 marks, we will discuss some theoretical aspects and also some problematic parts. So theoretical aspects contains some definitions. Some commonly used definitions are, the one is steady flow. The flow for which the quantity of fluid flowing per second is constant is known as steady flow. In this flow, there is no change in velocity, there is no change in pressure, and also there is no change in density. Therefore, dV by dt is equal to 0, dP by dt is also is equal to 0, and d rho by dt is also is equal to 0. On the other hand, the another flow is called as unsteady flow, which is opposite to of this. Means for this fluid, the quantity of fluid flowing per second is not constant. Means here the velocity changes, the pressure changes, and also the density changes. Hence we can write dV by dt is not is equal to 0, dP by dt is not is equal to 0, and d rho by dt is not is equal to 0. The other type of flow is uniform flow. So this is the flow for which the velocity at any given time does not change with respect to space. Hence mathematically we can write it as dV by ds is equal to 0. The opposite of this is non-uniform flow, for which the velocity at any given time changes with respect to space. Hence we can write dV by ds is not is equal to 0. The another type of flow is laminar flow. So this is the flow for which all the streamlines means a graphical representation of the flow path or fluid flow path. So all the streamlines are straight and parallel to each other, then we can write them as, or we can call it as a laminar flow. The next one is, opposite to this is turbulent flow. So in this flow, the fluid particles move in a random zigzag path. So another type of flow is compressible flow, for which the volume and density of the fluid is not constant, that is rho is not constant. And incompressible flow is the fluid in which the density and volume of the fluid is constant, that is rho is equal to constant. So another type of fluid is rotational flow. It is the fluid flow in which the fluid particles flowing along the streamlines also rotate about their own axis. Whereas in irrotational flow, the fluid particles flowing along streamlines do not rotate about their own axis. So another type of classification of flow is one-dimensional, two-dimensional, and three-dimensional flows. So one-dimensional flow is the flow in which velocity of the flow is a function of time and one space coordinate, usually x. That is, u is a function of x, whereas v is equal to 0 and w is equal to 0. In a two-dimensional flow, the velocity of flow is a function of time and two rectangular spaces, that is coordinates x and y. Therefore, u is a function of x and y, and phi is a function of x and y, whereas w is equal to 0. In three-dimensional flow, the velocity of flow is a function of time and also the function of three space coordinates. They are x, y and z. That is, u is a function of x, y, z, phi is also a function of x, y, z, and w is also a function of x, y, z. The very important basic equation in this chapter is called as equation of continuity, or which is also called as continuity equation. It is the basic equation of the hydraulics or fluid dynamics. So, continuity equation is based on the principle of law of conservation of mass. So, the figure is showing a tapered pipe through which the fluid is flowing. We have two sections, section 1-1 and section 2-2. The velocity at section 1-1 is V1 and the area of the pipe at section 1-1 is A1, whereas V2 and A2 are the corresponding values for the sections 2. Hence, the rate of flow at section 1-1 is given by A1 into V1. Similarly, the rate of flow at section 2-2 is given by A2 into V2. And according to the law of conservation of mass, the rate of flow at 1-1 is also is equal to the rate of flow at section 2-2. Therefore, A1 V1 is equal to A2 V2. So, this equation is known as a continuity equation. It is a very important question from the examination point of view. Sometimes you will ask, define the rate of flow. The rate of flow is also known as a discharge. So, rate of flow or discharge is defined as the quantity of fluid flowing per second. Means Q is equal to A into V. So, A is area meter square and V is velocity meter per second. Hence, the unit of discharge is meter cube per second, but practically it is also known as, it is now measured as liter per second. Sometimes in the problem, he will give the discharge in terms of liter and we have to convert this into meter cube per second. For that, we have to know that 1 meter cube is equal to 1000 liters. And the fluid which is flowing is having the different forms of energies. He will ask the question, what are the different forms of energies possessed by the fluid in motion? The fluid in motion is consisting of three forms of energy. They are a potential energy, that is PE, second is kinetic energy, that is KE, and third is pressure energy, that is called as PE. Potential energy is the energy possessed by the liquid particles by virtue of its position. Hence, it is called as PE is equal to Z. Usually, potential energy is represented by Z and measured as meters of fluid. The unit is meters of fluid. And kinetic energy is the energy possessed by the liquid particles by virtue of its motion. Usually, it is given by kinetic energy is equal to V square by 2G meters of liquid. And pressure energy is the energy possessed by a liquid particle by virtue of its existing pressure. Hence, it is given as P by W. W is called the specific weight of the fluid. Usually, potential head, usually they are expressed in terms of head also. Potential head, Z meter, kinetic head, P square by 2G meter, and pressure head is P by W meter. Hence, the total head or total energy of the liquid in flow is E is equal to Z plus V square by 2G plus P by W meters of water. The basic fundamental equation given by the Bernoulli for the fluid which is in motion, and this equation is known as Bernoulli's theorem. Sometimes you will ask for 5 marks, state and explain Bernoulli's theorem. The Bernoulli's theorem states that, so Bernoulli's theorem is applicable for the flow which is steady, frictionless and incompressible. Therefore, the statement is like that. In a steady flow of frictionless, incompressible fluid flow system, the total energy of the particle remains constant. So, here what you have to remember is the total energy of a particle remains constant. The total energy of what? Total energy of a steady flow of a frictionless, incompressible fluid flow system. Hence, it can be explained by the following figure, in which we are seeing a tapered pipe represented by the two sections 1, 1 and 2, 2, and a common line is drawn at the bottom, that is called as datum line. Section 1, 1 is at a height of Z1 meter, whereas section 2 is at a height of Z2 meter. P1 is the pressure at section 1, P2 is the pressure at section 2, V1 is the velocity at section 1, 1, and V2 is the velocity of the fluid at section 2, 2. So this is a representation of a figure, and we know that the loss of potential energy plus work done by pressure is equal to gain in kinetic energy. The loss of potential energy is W into bracket Z1 minus Z2. The work done by pressure is W by W into bracket P1 minus P2. And the gain in kinetic energy is W divided by 2Ag into bracket V2 square minus V1 square. Taking common W from both the sides, we can write Z1 minus Z2 plus P1 by P2 by W is equal to V2 square by V1 square by 2G. Or taking negative on one side and positive on the other side, we can write Z1 plus V1 square by 2G plus P1 by W is equal to Z2 plus V2 square by 2G plus P2 by W. That is, energy at section 1, 1 is equal to energy at section 2, 2. So this is the explanation for a Bernoulli statement. So for this statement of Bernoulli, we have assumed some things. He may ask the question, what are the assumptions made in the Bernoulli's theorem? So Bernoulli's theorem, as you know, that in a steady flow of frictionless, incompressible fluid flow system, the total energy of a particle remains constant. And for this derivation, the following assumptions are made. The first one is flow is steady. It is a steady flow. Second, it is an ideal fluid. And the flow is homogeneous and incompressible. The flow is also irrotational. The flow is uniform over the section, and there is no loss of energy during the flow. These are the 6 assumptions. That is, it is a steady flow, the fluid is ideal, the flow is homogeneous and incompressible, the flow is irrotational, the flow is uniform all over the section, and there is no loss of energy during the flow. Then another important question what you can expect is, what are the different applications of Bernoulli's theorem? So Bernoulli's theorem is used in venturimeter, which is used to determine the discharge, as well as in orifice meter, pitot tube. And some practical applications are aeroplane wings, atomizers and chimney, where all these things are working on the principle of Bernoulli's theorem. Now, this theorem has got some limitations. What are the limitations of Bernoulli's theorem or Bernoulli's equation? So actually, the velocity of fluid is maximum at the center of the pipe, and it decreases on either side of the center because of the friction. But we assume that the mean velocity of the liquid should be taken into account. Usually the velocity we take only at the center, but actually we have to consider the mean velocity because it is changing from top of the pipe to the center of the pipe. Therefore, mean velocity has to be considered, but we have taken the velocity only at the center of the pipe. Second limitation is, actually there are some external forces like friction force which affects the flow. Hence, all these forces are to be neglected. We have not considered actually the friction force also into the derivation. The third assumption is, in turbulent flow, some kinetic energy is converted into the heat energy, and for this viscous flow, the energy loss due to the shear force also takes place, which is not taken into consideration. And the another limitation is, for curved path, the energy due to centrifugal force should be taken into account, which is not considered during the derivation. So these are some limitations of Bernoulli's theorem. The first limitation is, we have to consider the mean velocity, whereas we have only considered the velocity at the center of the pipe. Second one, some forces due to kinetic energy and other is taken into account, but they are not considered. And the next one is conversion of kinetic energy into heat energy, and also the viscous flow losses were not considered. That has to be taken into consideration. And for curved path, the centrifugal force is also an additional force to be considered. We have not taken into consideration. Now we will come to the some applications and explanation for the applications. The first one is explain the principle of venturimeter with a neat sketch. Usually it is asked for 5 to 7 marks. So figure is showing you the venturimeter. You know venturimeter means it is a device which is working on the principle of Bernoulli's theorem. It is used for measuring the discharge at a point. So it is having 3 parts. The first one is known as converging part, in which the diameter of the pipe goes on decreasing. Second part is called as a throat, which is the narrowest part or minimum area where it is existing, and then after that there is a diverging cone, and on the left side is upstream, water is flowing to the downstream on the right side. So here the U2 manometer is connected between the converging and the throat part. As the pressure at 1 is less and the pressure at 2, means actually the difference in the mercury is represented by the height h. The height is the difference in the mercury level. So when the fluid is flowing between 1 and 2, that is converging zone, its velocity increases. So this increase in velocity decreases the pressure considerably. And when the fluid flows between 2 and 3, there is a deceleration and decrease in the velocity, which increases the pressure. The actual discharge is determined by using this venturimeter. This is about the explanation regarding the venturimeter. I have not taken the equation for this. Will take after another question. What about the derivation or equation of a venturimeter? Another important question you can expect is explain the working of orifice meter. So figure is showing you the orifice meter. Orifice meter means a orifice plate, a circular plate having a small hole at the center. The figure is showing. The D, capital D is representing the diameter of the pipe. Small d is representing the diameter of the orifice plate. It is connected at the in the pipe, means here the streamline flow is also showing. It is giving you the narrow path at the orifice hole, and then it is increasing. So the space where the area is very less is called as vena contracta diameter. It is the space where the minimum diameter is existing. So it is a device used for measuring the rate of flow, or you can also call it a discharge through the pipe. Again, it is working on the principle of Bernoulli's theorem or Bernoulli's equation, and the plate restricts the flow, which causes the pressure drop. When the fluid is flowing through this pipe, there is a restriction due to which the pressure drop takes place. And this pressure can be measured by using the manometer, which is connected between the two ends, and this flow rate is given by the equation. Actual flow Q actual is CD into A1 A2 divided by under root of A1 square minus A2 square into root of 2GH. CD is called as coefficient of discharge, A1 diameter of the pipe, A2 diameter of the orifice plate, H is the mercury level difference between the two tubes of the manometer. So another important application of this Bernoulli's theorem is pitot tube. Figure is showing you the pitot tube. So it is a right angled pipe inserted in between the flow in the pipe. It is a device used for measuring the velocity of flow at any point in a pipe. If you want to measure the velocity, we are using the pitot tube. It is working again on the principle of Bernoulli's equation. The fluid rises up in the tube as shown in the figure due to the conversion of kinetic energy into potential energy. Capital H is the height of the fluid in the pipe from the center, and small h is rise of the fluid above the pipe in the pitot tube. So applying Bernoulli's equation here, what we can write here is h plus v square by 2g is equal to h plus h. Cancelling capital H on both sides, what we will be getting is h is equal to v square by 2g, or v square is equal to 2gh, or v is equal to under root of 2gh. Hence you can measure the velocity of flow at any point in the pipe by using pitot tube. Some of the commonly definitions you can expect in the examinations are coefficient of discharge. It is called as CD. It is the ratio of actual discharge to a theoretical discharge. CD is equal to Q actual divided by Q theoretical. Second one is coefficient of resistance, that is called as CR. It is a ratio of loss of kinetic energy to the actual kinetic energy. The third is coefficient of velocity CV. It is the ratio of actual velocity of jet at vena contracta. I told you vena contracta means it is the place where the area is very minimum. Actual velocity of jet at vena contracta to the theoretical velocity of jet, that is called as coefficient of velocity. Then coefficient of contraction CC. It is the ratio of area of jet at vena contracta divided by area of orifice. Now here we will discuss about the expression for discharge through the venturimeter. As already you know, venturimeter is a device used to measure the discharge. It is consisting of three parts: a converging zone, the throat, and a diverging zone. Figure is showing the same thing. And V1 is the velocity of water at section 1,1, P1 is the pressure at 1, and Z1 is the datum head at 1,1. The corresponding values at 2,2 are V2, P2 and Z2. And we know that according to the Bernoulli's theorem, the total energy remains the same. That is Z1 plus V1 square by 2G plus P1 by W is equal to Z2 plus V2 square by 2G plus P2 by W. If the differential manometer contains liquid, this is very important. If the differential manometer contains liquid heavier than the liquid flowing through the pipe, then what we can write here is H is equal to. In the question paper, the problem, he will give the difference in the height, but it is not H. It is to be taken as X. And H has to be calculated in two different cases. In case 1, if the manometer is containing the liquid heavier than the liquid flowing through the pipe, then H is equal to X into bracket SH divided by SO minus 1. And if the manometer contains the liquid lighter than the liquid in the pipe, then H is equal to X into bracket 1 minus SL by SO. So friends, you please note that in the problems, if the difference in the manometer is given, mercury level is given, you should not take it as H. H has to be calculated separately by using these two equations depending upon which type of liquid is present in the manometer and which type of liquid is present in the pipe. And here I told you X is the difference of heavier liquid column in U-tube, whichever is the heavy one. SH, specific gravity of heavier liquid in the U-tube. SL, specific gravity of lighter liquid in the tube. And SO is specific gravity of liquid flowing through the pipe. So this is about the important. You can expect usually one problem based on usually a venturimeter, sometimes from the orifice meter. A simple equation, a question carrying 7 marks up to sometimes 10 marks. Definite question. If you refer the previous question paper, the problems are very simple. Even from the syllabus, the important questions, I have solved all the problems. You please go through whatever the problems I have solved and you read it again. Once again you go through the notes and you will come to know how to solve the problems. Regarding the problem solving, if you are having any difficulties, so please ask me regarding the problems. But before that, you just go through that time. I hope this will be very helpful to you to revise the chapter again. Please remember this chapter carries 25 marks. Okay. Thank you.